So we're looking at related rate problems. We already started this. I pulled up again how to solve these related rate problems and how to go about the process. First thing you're going to do is you're going to read through the problem really carefully, and then you're going to go through and you're going to start pulling out the information. So assign symbols, oops, that's not the color I wanted. Assign symbols to the variables involved in the problems. And we're going to draw a picture. That's usually really helpful if we aren't given a picture to help us. We're going to state in terms of the variable the information that is given and the rate to be determined. So we're going to look at all of this information. We're going to figure out what's our rates of change. So what are derivatives in the information given? What are the values when we're not given the derivative? We're going to find an equation that relates the variables, all the variables together. And then we're going to use implicit differentiation. And within that implicit differentiation, you're using your chain rule and you're differentiating both sides of the equation that we found in terms of the independent variable, which is normally in terms of time. And then once we've done that, we have all this information that we were given and we pulled out that we can go back in and plug into that derivative and figure out the unknown. Okay, so let's look at another example where we're dealing with a triangle, but a little different. So that last example we looked at yesterday was looking at the rate of change of the angle as the rocket was lifted off. So here. Okay, let me just read this off to you and then we'll pull out important information and we'll label it. So we have a plane is 750 meters in the air and flying parallel to the ground at a speed of 100 meters per second and is initially 2.5 kilometers away from the radar station. At what rate is the distance between the plane and the radar station changing initially? Okay. Okay, so we're given that a plane is 750 meters in the air. Okay, so off the ground, this is 750 meters. I really can't draw, but okay, so here's our plane. And it's flying parallel to the ground. And the speed is 100 meters per second. And we're also given that it is 2.5 kilometers from the radar station. Okay, so this is 2.5. We have a problem here because this is in meters and this is in kilometers. And so we want them to be in the same units, and this is meters per second. So we want to change this 2.5 kilometers, and that kilo means 1,000. So 1,000 times 2.5, that would change this to 2,500 meters. Away from this radar station. And that plane is coming closer and closer, and we can right now make this right triangle. So let's label the hypotenuse. Maybe we can call it Z. We can figure out what this initial distance is by using our Pythagorean theorem. So we know that z squared is equal to 2,500 squared plus 750 squared. And we're going to want to take the derivative, not the derivative. We are going to want to take the derivative, but not right quite yet. We want to take the square root of both sides. So 2,500 squared plus 750 squared. That gives us the square root of 6,812,500. Let's get an approximate. So this is approximately I have 2,610 meters. But this plane is changing, right? It's getting closer and closer to the station. Notice that the plane right now, it's coming closer to the radar station. And so remember, there's a difference. This vectors include direction, and that direction is, so our speed is actually going to be a negative. So maybe we can do ds dt equals negative 100. Okay, so we want to go in here and we want to set up an equation that relates all of this information. This is going to be changing as the plane is coming in here. And so is this z value. That's also going to be changing. The one thing that's not going to be changing is this height. So maybe we can call this x of t. This is z of t. So those are both changing with time. So we have z squared is equal to x squared plus 750 squared. So let's go through and let's take the derivative. Remember, these are functions in terms of time. So when we're going to do implicit differentiation, we have to take the derivative of the inside. So the derivative of z squared is 2z times dz dt is equal to derivative of x squared is 2x times dx dt. And the derivative of our constant is 0. We're trying to find what is the rate. Let me just go back to what we're trying to find. We're trying to find at what rate is the distance between the plane and the radar station changing. So we're looking at this rate of change. So plugging this in, we want to solve for this value. This distance is changing, actually. This is the one we want to see. So we have dz dt is equal to 2x all over 2z dx dt. These always make me think. So let's reduce down and let's plug in what we know. Oops. And it's probably because this is what was confusing me, that this rate of change, how we're coming in here, this is our X value. So this was dx dt. Okay, so let's plug in what we know. We know what our X value is. So we have the rate of change, dz dt. This X value at the initial piece is equal to 2,500. All over our Z value, which we just found. Z was approximately this 2,610, all times dx dt. And our dx dt, the rate of change of X, is equal to -100. And so we can go in here and we can simplify. I know I can at least cancel out one of those zeros. And the rate of change, this rate of change in this distance of Z initially is, so let's just plug it in. So we have 250 divided by 261, and we're going to multiply that by -100. Which is equal to approximately 95.8 meters per second. And it's negative. Okay, so that distance right now, as the plane is coming in, that distance is shrinking. So they had one other bit of a question in here on this problem, and they want to know, how about what is the rate of change when of the distance between the radar station and the plane when the airplane passes the radar station a minute later. Okay, so now it's going away from the radar station. So we have the still distance is 750 meters. We need to figure out what this distance is in here. And we want to figure out what this distance. Actually, I kind of made this a little off. This is still 750. Our plane's going this way. And this is the distance. I'm going the wrong thing. Okay, so this is 750. We can figure out what this distance is. We know distance equals rate times time. The rate that this plane is going was 100 meters per second. So our distance is going to equal 100 per second though. And our time here was 1 minute. So we have to change that in terms of seconds. So this would equal 60 seconds. So we know that this distance in here then is 6,000. And we have to figure out what this distance is here. So our X value when we're looking at this is 6,000. Our Y value, this distance in here, is 750. And we can find out what Z is by using the Pythagorean theorem. So Z squared is equal to 6,000 squared plus 750 squared. Let's just take the square root of that. So 6,000 squared plus 750 squared is the square root of 36,562,500. Which is approximately 6,047 miles away. Not miles, meters. Because we're going to do the exact same thing that we were doing before. Our rate of change, dx dt, because it's going away, it's positive. So we're going to look at, we know z squared is equal to x squared plus 750 squared. That's not changing. So we get 2z dz dt equals 2x dx dt. Taking the derivative of both sides. We actually really did that work before, so we know dz dt, dividing both sides by 2x was the same, 2z, we get x dx dt all over z. So we're going to plug in what we know when it's a minute away from the radar station after it passes it. So the rate of change of that distance between the radar station and the plane is equal to our X value, which we said was 6,000. All times the rate of change, which 100 meters per second, divided by Z, which we found to be approximately 6,047. If you do that, that is approximately 99.2 meters per second. Okay. So questions on that one?